Hello there, and welcome to Simple Science for Sleep. There are places on Earth where the ground remembers everything, every tremor, every shift, every moment when the planet held its breath before screaming. These places don't forget. They simply sleep. And in their sleep, they dream of fire, of skies turned black, of winters that lasted years, of the day when everything alive had to choose between adapting or disappearing. We stand on these sleeping giants every day, never knowing that beneath our feet lies a force that has erased civilizations, reshaped continents, and brought life itself to the edge of extinction more than once. Tonight, we drift into the deep places of Earth, where forces beyond imagination have shaped every living thing. We're going to walk through time itself, visiting moments when our planet opened up and reminded everything alive who's really in charge. But don't worry, this is a story about survival, about resilience, about how life, no matter how hard things get, always finds a way forward. Get comfortable. Let the weight of your body sink into wherever you're resting. We're about to explore something extraordinary together. Before we begin this journey, if these quiet explorations bring you peace, if you enjoy drifting off to sleep while discovering the wonders of our world, consider liking this video and subscribing to the channel. You'll be joining thousands of other curious souls who find comfort in these stories, and I'd love to know where you're listening from tonight. Drop a comment telling me your location and what time it is there. It's amazing to think we're all scattered across the globe, yet here we are, sharing this moment together. Now, let's talk about supervolcanoes. The word itself sounds dramatic, doesn't it? Super, like something from a movie. But the reality is far more incredible than any fiction. A supervolcano isn't just a big volcano. It's a completely different beast. Think of it this way. A regular volcano is like a firecracker, loud, bright, a little dangerous if you're too close. A supervolcano is like comparing that firecracker to enough dynamite to level an entire city. The difference isn't just size, it's the fundamental nature of what happens. Scientists measure volcanic eruptions using something called the Volcanic Explosivity Index. It's a scale from 0 to 8. Most eruptions you hear about on the news, the ones that disrupt air travel or force evacuations, those rate around a 4 or 5. They're serious, they can be deadly. But a supervolcano eruption rates an 8, the highest level. And here's what that means in real terms. When a supervolcano erupts, it doesn't just affect the area around it, it affects the entire planet. We're talking about enough ash to bury entire states under feet of grey powder. Enough gases to change the temperature of the whole world. Enough force to leave a scar on Earth that lasts for millions of years. The crater left behind, called a caldera, can be dozens of miles across. You could fit entire cities inside it. These aren't just mountains that explode. They're places where Earth's crust is thin, where massive chambers of molten rock build up pressure over thousands of years. And when they finally let go, when that pressure finds a way out, the results reshape everything. But to understand these giants, we need to go back, way back, before humans walked upright, before the ice ages, to a time when Earth was still figuring out what it wanted to be. 28 million years ago, in what we now call Colorado, something was building. Deep underground, miles below the surface, a massive chamber of molten rock was growing. It had been filling for thousands of years, slowly, patiently, like a balloon being inflated, one breath at a time. The rock above it was strong, but even the strongest stone has its limits. Imagine holding your breath. The pressure builds in your chest. Your body wants to release it. Now, imagine that pressure building not for seconds, but for millennia. That's what was happening beneath the ground in ancient Colorado. The magma chamber was enormous, perhaps 20 miles across. The heat down there would melt steel in seconds. The pressure was beyond anything we can recreate in a lab. And then, one day, the rock above couldn't hold anymore. What happened next was the La Garita eruption, and it remains one of the largest volcanic events we know about in Earth's history. To understand just how massive this was, let's put it in perspective. Mount St. Helens erupted in 1980. You might have heard about it or seen pictures of the devastation. That eruption was powerful enough to flatten forests for miles, to send ash across several states, to change the shape of the mountain itself. It rated a 5 on the Volcanic Explosivity Index. La Garita was 5,000 times larger. Let that sink in for a moment. 5,000 times. It's almost impossible for our minds to grasp that kind of scale. But let's try to picture it together. When La Garita erupted, it didn't just send ash into the sky. It ejected enough material to bury the entire state of California under a layer of rock and ash more than 3 feet deep. The eruption column, that massive plume of gas and debris, reached into the stratosphere. Some scientists think it might have punched through into space itself. The explosion was so violent that it created a crater, a caldera, that measured 22 miles across and 47 miles long. You could fit a small country inside it. The sound would have been heard thousands of miles away. The shockwave rippled through the atmosphere, circling the globe multiple times. But here's where it gets even more incredible. The ash from this single eruption spread across half of what is now North America. From Colorado, it drifted east and south, carried by winds that choked on the sheer volume of debris. In places like Kansas and Nebraska, the ash fell like snow, except it wasn't cold and it wasn't water. It was hot, abrasive volcanic glass that buried everything it touched. Animals that breathed it in found their lungs coated with a substance that turned to concrete when it mixed with moisture. Plants were smothered under the weight. Rivers and streams turned grey with sediment, killing fish by the millions. The sun, for months or perhaps years afterward, was dimmed by the particles floating in the atmosphere. Temperatures dropped. Growing seasons shortened. It was a different world than the one that existed before. Yet this eruption happened in a time when mammals were still relatively new to being the dominant life forms on land. The dinosaurs had been gone for about 40 million years by this point. In their place, strange creatures roamed. Early horses, no bigger than dogs. Saber-toothed cats with fangs like daggers. Giant ground sloths that could rear up to the height of a giraffe. Many of them didn't survive the eruption and its aftermath. But some did. They found shelter in valleys where the ash didn't penetrate as deeply. They adapted to eating different plants, tougher vegetation that could grow in poor soil. They migrated away from the devastation, following instincts older than thought itself. Life, even when faced with overwhelming destruction, finds pockets of possibility. It squeezes through the narrowest of gaps between extinction and survival. And over time, slowly, the land began to heal. Plants grew through the ash layer. Animals returned. The caldera filled with water and sediment, hiding the evidence of catastrophe beneath new layers of earth. But this ancient giant was just the first we know about in detail. There have been others, scattered across time and geography, like markers on a map of Earth's violent history. And one place in particular has written its story in fire more than once. If you've ever visited Yellowstone National Park, you know it as a place of beauty. Geysers shooting water into crisp mountain air, hot springs colored like rainbows, buffalo grazing in meadows that stretch to the horizon. It feels peaceful, safe, the kind of place where you go to escape the noise of modern life and reconnect with nature. But beneath that peaceful surface, something massive is waiting. Yellowstone sits on top of a hotspot, a place where a plume of superheated rock rises from deep within Earth's mantle. This plume has been in the same spot for millions of years, even as the North American continent slowly drifts over it. And every few 100,000 years, the pressure builds to a breaking point. 2,100,000 years ago, Yellowstone erupted for the first time that we know of. This event is called the Huckleberry Ridge eruption, named after the geological formation it created. The name sounds almost gentle, doesn't it? Like something you'd find in a children's story. But there was nothing gentle about what happened. Picture the Yellowstone area as it was back then. No geysers, no hot springs, just a landscape building toward catastrophe. The magma chamber beneath the surface had been filling for longer than our species has existed. The ground above it was bulging upward, rising inch by inch, year by year. Trees that grew on the slopes found themselves suddenly tilted. Streams changed course as the land warped beneath them. Then came the earthquakes. Not just one or two, but swarms of them, hundreds, thousands. The ground shook constantly, a reminder that something below was trying to break free. Animals sensed it. They became restless, moving away from the area in great migrations that followed instinct rather than reason. And then the earth opened. The Huckleberry Ridge eruption released 600 cubic miles of material. To put that in perspective, imagine every building in every major city on Earth, crushed down and compacted. You still wouldn't have enough material to equal what came out of Yellowstone that day. The eruption column rose higher than the cruising altitude of modern jets. The sound was the loudest thing that had ever happened in that part of the world. Within hours, ash began falling across the western United States. In some places close to the eruption, it piled up dozens of feet deep. The weight of it collapsed cave systems. It buried forests while they still stood, preserving them in stone like some vast natural museum. Farther away, in places like Iowa and Missouri, the ash fell like a grey snow, coating everything in a layer just inches thick. But even that was enough to devastate the ecosystem. The ash itself was dangerous in ways that might not be obvious. under a microscope, volcanic ash looks like tiny shards of glass. Sharp, abrasive. When animals breathed it in, it scraped their lungs raw. When it mixed with water in their bodies, it formed a cement-like substance. Many animals suffocated, their airways blocked by this deadly mixture. Plants couldn't photosynthesize through the layer of ash that coated their leaves. They withered and died, even far from the eruption site. And when the plants died, the herbivores that depended on them followed. Then the carnivores that hunted those herbivores. The entire food chain collapsed, like dominoes falling in slow motion. But some life survived. In the far reaches of the continent, beyond the worst of the ashfall, animals continued their lives. Small mammals that could burrow underground found protection from the choking air. Birds flew to cleaner skies, though many didn't make it. Fish in deep lakes survived where their shallow water cousins perished. The aftermath lasted for years. The ash in the atmosphere reflected sunlight back into space, cooling the planet. Summers became shorter. Winters stretched longer. Ice formed in places it had never been before. But gradually, decade by decade, the atmosphere cleared. Rain and wind eroded the ash layers. Seeds that had laid dormant began to sprout. Life crept back into the devastated zones, tentative at first, then with growing confidence. The caldera left by this eruption measured 50 miles across. It was so large that early geologists didn't even recognize it as a volcanic feature. They thought it was just a valley, a natural depression in the landscape. It took decades of careful study to realize what had really happened there. But Yellowstone wasn't done. Not even close. The hotspot beneath it was still there, still active, still building pressure for the next chapter in its explosive history. 800,000 years passed. 800,000 years of relative quiet, of healing, of life rebuilding itself across the landscape. The caldera from the first eruption had long since filled in with sediment and new volcanic material. Forests grew, rivers carved new paths. Animals returned and flourished. To any observer, Yellowstone would have looked like any other mountainous region, beautiful and peaceful. But deep below, the hotspot never stopped working. Magma continued to rise from the mantle, pooling in massive chambers beneath the surface. The pressure was building again, invisible and patient. The Earth has all the time in the world. It doesn't rush. 1,300,000 years ago, Yellowstone erupted again. This event is called the Mesa Falls eruption, and while it wasn't quite as large as the first one, it was still catastrophic beyond anything in recorded human history. This time, the eruption released 280 cubic miles of material. Picture a cube of rock and ash that stretches 40 miles on each side. Now, imagine all of that being thrown into the atmosphere in a matter of hours. The pattern was similar to before, but the location had shifted slightly. The North American plate had moved a bit over the hotspot, so this eruption happened in a different spot than the first one. This created a new caldera, overlapping with parts of the old one. Yellowstone was literally reshaping itself through violence. The ash spread across the continent once more, following the prevailing winds. But this time, life was perhaps slightly better prepared. Evolution had spent 800,000 years creating species that were more resilient, more adaptable. Animals that could survive on minimal food. Plants with seeds that could lay dormant for years, waiting for conditions to improve. Still, the death toll was immense. Entire species that had thrived in the region were wiped out. Others were pushed to the edge of extinction, surviving only in small pockets far from the devastation. The climate cooled again as ash particles blocked sunlight. Growing seasons shortened. Migration patterns were disrupted. But here's what's fascinating. Between these eruptions, between these moments of catastrophe, life didn't just survive, it thrived. The volcanic soil left behind by each eruption was incredibly rich in minerals. Once the immediate danger passed, once the ash settled and began to break down, it created some of the most fertile ground on Earth. Plants that managed to take root in this soil grew stronger, healthier. They supported larger populations of herbivores, which in turn supported more predators. Each eruption was a reset button, but not a complete erasure. Life learned, it adapted. Species that survived carried genetic traits that made them more resilient. Behaviors that helped animals escape the danger zones were passed down through generations. Evolution wasn't just happening despite these catastrophes. In some ways, it was happening because of them. The time between eruptions also revealed something important about the rhythm of these events. Scientists studying Yellowstone noticed a pattern emerging. About 800,000 years between the first and second eruptions. This suggested that the hotspot operated on a cycle, building and releasing pressure at relatively regular intervals, which led to an obvious question. If there was a first eruption, and then a second, would there be a third? The answer, as it turned out, was yes, and it would create the Yellowstone we recognize today. 640,000 years ago, Yellowstone woke up for the third time. This eruption, called the Lava Creek event, would be the one that shaped the landscape we see today. The one that created the massive caldera that now holds geysers and hot springs. The one that tourists visit without realizing they're standing inside the scar of a catastrophe. By this point in Earth's history, life had become more complex and diverse. Mammoths roamed the plains, their thick fur protecting them from Ice Age cold. Giant beavers the size of bears built dams across rivers. Dire wolves hunted in packs. And in Africa, early human ancestors were just beginning to experiment with stone tools, though they wouldn't reach North America for hundreds of thousands of years yet. The Lava Creek eruption released about 240 cubic miles of material, slightly smaller than the first eruption, but still incomprehensibly massive. The violence of it created a caldera that measured 30 miles by 45 miles. If you stood at one end, you couldn't see the other side, even on a clear day. The walls of this depression rose hundreds of feet above the floor. What makes this eruption particularly interesting is what happened afterward. Unlike the previous two events, we have more detailed geological evidence of the recovery process. The ash layers are closer to the surface. They're easier to study, and they tell a story of resilience that's almost beautiful in its stubborn insistence on continuing. Within decades, perhaps even years, pioneer species began to colonize the ash fields. These weren't the same plants that had grown before. They were hardy, aggressive species that could tolerate poor soil and harsh conditions. Grasses with deep root systems that could punch through the compacted ash. Small shrubs that could survive on minimal nutrients. Mosses and lichens that broke down the volcanic rock into something more like soil. These pioneer species did something crucial. They started the process of transforming dead ash into living earth. When they died, their organic matter mixed with the minerals in the ash. Slowly, a thin layer of actual soil began to form. And once that happened, other plants could move in. Plants with more complex needs. Plants that supported insects. And insects brought birds. Birds brought seeds from distant places. Each addition made the ecosystem a little more complex, a little more stable. The animals that survived developed fascinating adaptations. Some species of ground squirrels, for example, developed the ability to eat plants that were toxic to other animals. This gave them access to food sources that competitors couldn't touch. Certain birds learned to build nests in the sparse vegetation, where predators were easier to spot. Evolution was happening in real time, driven by the harsh new reality. The caldera itself became a unique environment. The volcanic heat that had caused the eruption didn't disappear. It remained beneath the surface, warming the ground. This created thermal features like the ones we see today. Hot springs bubbling with mineral-rich water, geysers erupting on predictable schedules. These features became oases in an otherwise harsh landscape, places where life could cluster and thrive. Rivers flowing into the caldera deposited sediment, slowly filling it in. Lakes formed and dried up, formed again. Each layer told a story, preserved in stone like pages in a book. Scientists reading these layers can see the climate changes, the floods, the droughts, all recorded in microscopic detail. But while Yellowstone was sleeping, exhausted from its third awakening, another giant on the other side of the world was preparing to write one of the most dramatic chapters in the history of life on Earth. The island of Sumatra sits in Indonesia, part of a chain of volcanic islands strung along the Pacific Ring of Fire. It's a place of intense beauty, where tropical rainforests meet active volcanoes, where orangutans swing through canopies and tigers prowl the undergrowth. The land is fertile, fed by volcanic soil. People have lived here for tens of thousands of years, drawn by the richness of the earth. But this fertility comes at a price. Sumatra sits at the meeting point of two massive tectonic plates, the Indo-Australian plate sliding beneath the Eurasian plate. This collision zone generates enormous geological forces. Mountains rise, earthquakes shake the ground, and magma, squeezed from the rocks by heat and pressure, rises toward the surface. In the northern part of Sumatra, there's a place that looks like a massive lake. Lake Toba, one of the largest volcanic lakes in the world. It's beautiful, surrounded by mountains, its waters clear and blue. Tourists visit to swim and relax. Locals fish its depths. But this lake is actually a caldera, the scar left by an eruption so massive it almost ended humanity. Toba wasn't always quiet. It has a history of eruptions stretching back over 1 million years. About 1.2 million years ago, it erupted with significant force. Not quite a supervolcano event, but powerful enough to reshape the landscape. Then, around 840,000 years ago, it erupted again, this time reaching that threshold of catastrophe we call a VEIIT eruption. These earlier eruptions left their marks. Ash layers buried deep in the geological record, calderas that filled with water and sediment. Each eruption was followed by long periods of quiet, where life recovered and flourished. The pattern was similar to Yellowstone, a cycle of destruction and renewal playing out over hundreds of thousands of years. Between eruptions, the region was paradise. The climate was warm and wet, perfect for life to explode in diversity. Rainforests grew thick and tall. Animals evolved in isolation, creating species found nowhere else on Earth. Early human ancestors migrated through the area, following game and edible plants, establishing small communities along rivers and coastlines. The magma chamber beneath Toba was enormous, perhaps even larger than the ones beneath Yellowstone. It sat relatively close to the surface, just a few miles down. The heat from it warmed the ground above, creating hot springs and fumaroles, places where gases hissed from cracks in the earth. These were warning signs, but to the animals and early humans living there, they were just features of the landscape, as normal as rain or sunshine. As the chamber filled over thousands of years, the pressure built steadily. The ground above it began to bulge, rising slowly like bread dough in an oven. Cracks formed in the rock. Small earthquakes became more frequent. Animals grew nervous, their instincts detecting something wrong even if they couldn't understand what. By 74,000 years ago, the magma chamber was full. The rock above it was stretched to its absolute limit, thin and fragile. The pressure was looking for any weakness, any fault line or crack where it could escape. And when it found one, when the rock finally failed, the result would be the most powerful volcanic eruption in the last 2 million years. An eruption that would bring life on Earth closer to extinction than it had been since the dinosaurs disappeared. And then everything changed. 74,000 years ago, the Earth beneath Sumatra split open. The eruption began with a series of massive explosions as superheated magma met groundwater. Steam expanded with such force that it shattered rock. The sound was beyond anything we can imagine. Some scientists believe it may have been the loudest sound in human history, loud enough to rupture eardrums hundreds of miles away. The eruption column rose into the stratosphere, punching through the atmosphere like a fist through paper. It carried with it 670 cubic miles of rock, ash, and volcanic debris. To understand this scale, imagine every mountain range on Earth ground down to dust and thrown into the sky. You'd still fall short of what Toba released in a matter of days. The ash fell first on Sumatra itself. Within hours, everything within several hundred miles was buried under feet of hot volcanic material. Entire forests were incinerated or crushed. Rivers boiled away. Animals that couldn't fly or run fast enough were entombed where they stood. The island was transformed into a grey wasteland, lifeless and choking. But Sumatra was just the beginning. The ash spread outward, carried by high-altitude winds. It fell across India like deadly snow, accumulating in places to depths of nearly 20 feet. Imagine standing in your house, and watching ash pile up outside your window, rising to the second floor, blocking out all light. The Indian subcontinent was buried under approximately 40 million tons of ash. The ash travelled even farther. It drifted east across Southeast Asia, west across Africa, north into China. Scientists have found toba ash layers in ice cores from Greenland, in deep sea sediments from the Indian Ocean, in cave deposits across 3 continents. The entire planet received a coating of volcanic debris. But the ash was only the first problem. The gases released by the eruption were perhaps even more devastating. Sulfur dioxide billowed into the stratosphere, where it reacted with water vapor to form tiny droplets of sulfuric acid. These droplets were the perfect size to reflect sunlight back into space. They created a veil around the entire planet, dimming the sun. Temperatures dropped. Scientists estimate the global average temperature fell by as much as 15 degrees Celsius in some regions. But averages don't tell the real story. In some places, particularly in the northern hemisphere, temperatures may have plummeted by 20 or even 25 degrees. Summer disappeared. Winter became permanent. This period is called a volcanic winter, and it lasted for years. Some models suggest the worst effects persisted for 6 years, with milder cooling lasting a decade or more. Plants couldn't grow without adequate sunlight. Photosynthesis slowed or stopped entirely. Grasslands died back. Forests went dormant. And when the plants died, everything that depended on them began to starve. Herbivores ran out of food. They grew thin, weak, unable to reproduce. Carnivores found fewer prey animals. They turned on each other, or starved as well. Entire ecosystems collapsed like houses of cards. Species that had thrived for millions of years were suddenly pushed to the brink of extinction. And among those species struggling to survive were humans. Our ancestors were scattered across Africa and parts of Asia. They lived in small groups, hunting and gathering, using stone tools and fire. They had survived ice ages and droughts, predators and disease. They were adaptable and clever, but toba tested them like nothing before. This is where the story gets really interesting. When geneticists look at human DNA, they see something unusual, something that sets us apart from almost every other species on Earth. We're remarkably similar to each other. A human from Norway and a human from Kenya have far fewer genetic differences than 2 chimpanzees from neighboring forests in Africa. This shouldn't be possible. We've spread across every continent, lived in vastly different environments, been separated for thousands of generations. We should be more diverse, not less. This similarity tells a story written in our genes. At some point in our past, the human population crashed dramatically. We went through what scientists call a genetic bottleneck, a moment when our numbers dropped so low that only a fraction of our genetic diversity survived. And the timing of this bottleneck matches perfectly with the Toba eruption. Before Toba, estimates suggest there may have been several 100,000 humans alive. We were spread across Africa and parts of Asia, living in scattered groups. We were still a relatively young species, but we were growing, adapting, spreading into new territories. Our future looked bright. After Toba, genetic evidence suggests the global human population may have dropped to as few as 3,000 individuals. Some estimates are even more dire, suggesting perhaps only 1,000 breeding pairs survived. Think about that for a moment. All of humanity, reduced to the population of a small town. Every human alive today, all 8 billion of us, descended from that tiny group of survivors. These survivors didn't all live in one place. They were scattered across the parts of the world that remained barely habitable. Some scientists believe the largest surviving population was in equatorial Africa, where the volcanic winter was slightly less severe. Other groups may have survived in coastal areas, where they could rely on seafood when land animals became scarce. A few hardy bands may have persisted in caves, using fire to stay warm through the endless winter. Imagine being one of those survivors. You've spent your entire life in a world that made sense. Animals followed predictable patterns. Plants grew in their seasons. The sun warmed the earth. Then, one day, the sky turns dark. The sun becomes a pale ghost. Ash falls like snow, but burns when you touch it. The temperature drops and keeps dropping. The animals you hunt disappear. The plants you gather wither and die. You have to make choices. Do you stay where you are, hoping conditions improve? Or do you move, searching for better territory? Both options are gambles. Both could mean death. But doing nothing certainly means death. So you move. You follow the coastlines where shellfish still cling to rocks. You hunt smaller animals, things you might have ignored before. Lizards, insects, anything with calories. You learn to preserve food, to make it last through the long, dark periods. You share with your group because alone, nobody survives. The groups that made it through had certain advantages. They had fire, which provided warmth and protection. They had language, which allowed them to share knowledge and coordinate hunting. They had tools, which made them more efficient. But most importantly, they had each other. Humans are social animals. We survive by cooperating, by sharing resources, by taking care of the young and the old. Still, most groups didn't make it. Most died out as the winter stretched from months into years. The genetic diversity we lost during this time will never be recovered. But humans weren't the only ones hanging on. The volcanic winter couldn't last forever. Slowly, over years and then decades, the sulfuric acid droplets in the stratosphere began to fall back to Earth. Rain washed them from the sky. The veil that had blocked the sun grew thinner. Light returned, weak at first, then stronger. Temperatures began to rise, creeping back toward normal. The long night was ending. But the world that emerged from this darkness was different, changed, empty in ways that would take thousands of years to fill again. Entire species had vanished. Others had been reduced to tiny populations, clinging to existence in scattered refuges. The landscape was quiet, in a way it had never been before. Yet life, as it always does, found a way forward. The first signs of recovery came from the plants. Seeds that had laid dormant in the ash, waiting for conditions to improve, began to sprout. These weren't the same plants that had dominated before. They were the hardy ones, the survivors, the species that could tolerate poor soil and harsh conditions. Grasses pushed through the ash layers. tough shrubs took root in the grey wasteland. These pioneer plants did something crucial. Their roots broke up the compacted ash, creating spaces for air and water. When they died, their organic matter mixed with the volcanic minerals, creating the first thin layers of new soil. It was a slow process, measured in decades rather than years, but it was happening. The dead landscape was slowly coming back to life. Animals followed the plants, small creatures at first, insects that could survive on minimal vegetation, rodents that could dig burrows and store food, birds that could fly long distances in search of resources. These animals brought something important with them: seeds. Stuck to their fur, carried in their digestive systems, seeds from distant places arrived in the recovering zones. Each new plant species made the ecosystem a little more complex, a little more stable. In the oceans, recovery happened faster. The volcanic winter had cooled the water, but marine life was more insulated from the temperature changes. Fish populations had crashed, but not disappeared. They rebounded relatively quickly, feeding on the nutrients that washed into the sea from the ash-covered land. Coastal areas, where marine and terrestrial ecosystems met, became refuges where life could rebuild. The surviving humans emerged from their sanctuaries cautiously. They followed the game animals as they migrated back into areas that had been dead zones. They gathered plants that were once again producing edible seeds and fruits. They rebuilt their populations slowly, generation by generation. The groups that survived carried knowledge that had been tested by the harshest conditions imaginable. They knew how to make fire in wet conditions, how to find food when it seemed there was none, how to keep their people alive through impossible winters. Other large mammals also recovered. Mammoths, which had nearly gone extinct, found new grazing lands in the recovering grasslands. Saber-toothed cats followed the herbivores. Bears emerged from caves where they had hibernated through the worst of it. Each species that survived had been through a filter, a test of their adaptability. The ones that made it through were tougher, more flexible, better equipped to handle change. The recovery took thousands of years, 10,000, 20,000. But eventually, the ecosystems rebuilt themselves. New forests grew, rivers ran clear again, the ash layers were buried under new soil, and life learned something important from this experience. Toba taught life a lesson, and life remembered. While Toba was reshaping the future of humanity, another supervolcano was writing its own story on the opposite side of the world. In what we now call New Zealand, in the heart of the North Island, a massive magma chamber was filling beneath the surface. This place would eventually be called Lake Taupo, but 26,500 years ago, it was about to experience one of the most powerful eruptions the region had ever seen. New Zealand is a young land in geological terms. It sits on the boundary between the Pacific and Australian tectonic plates, a collision zone that generates intense volcanic activity. The islands are volcanic through and through, built by eruption after eruption over millions of years. The landscape is dramatic, mountains rising sharply from the sea, geothermal features dotting the terrain. The Uruanui eruption, as scientists call it, released about 270 cubic miles of material. To put this in perspective for the region, imagine the entire North Island buried under several feet of ash and pumice. That's essentially what happened. the eruption column rose high into the stratosphere, visible from hundreds of miles away. But New Zealand at this time had no human observers. Humans wouldn't arrive on these islands for another 25,000 years. The witnesses to this catastrophe were the unique animals that had evolved in isolation. Giant flightless birds called moa, some standing 12 feet tall, roamed the forests. Massive eagles with wingspans over 9 feet hunted the moa. Reptiles that had changed little since the time of dinosaurs basked in the sun. When Taupo erupted, these creatures had nowhere to go. New Zealand is isolated, surrounded by vast stretches of ocean. There was no migrating to safer territories. Animals either survived where they were, or they didn't. The eruption was particularly devastating because it came in waves. The initial explosion was followed by pyroclastic flows, superheated clouds of gas, and volcanic debris that raced across the landscape at hundreds of miles per hour. These flows are among the most deadly volcanic phenomena. They incinerate everything in their path. Trees explode from the heat before the flow even reaches them. Animals die instantly, their bodies often preserved as casts in the ash. The flows from Taupo spread across the central North Island, filling valleys, climbing hills, leaving behind deposits that in some places were hundreds of feet thick. The ash from this eruption spread across the entire country and far into the ocean. Ships crossing the Pacific today sometimes dredge up sediment containing Oruanui ash, evidence of how far the debris traveled. The eruption also affected the climate, though not as severely as Toba. The southern hemisphere experienced cooling, shortened growing seasons, changes in rainfall patterns. For the animals that survived, usually those on the far edges of the South Island or on smaller offshore islands, the recovery was painfully slow. The central North Island was essentially sterilized. It would take centuries for plants to recolonize the ash fields. And when they did, the ecosystem that emerged was different from what had existed before. Some species never recovered. Others adapted to the harsh new conditions. The eruption created a massive caldera where the magma chamber had collapsed. Over time, this depression filled with water, creating the lake we see today. But beneath that peaceful surface, the magma chamber was already beginning to refill. The cycle wasn't finished. Taupo had another chapter to write, though it would wait thousands of years before doing so. In the year 232 CE, while the Roman Empire was near its height and the Han dynasty ruled China, something extraordinary happened in the Pacific. Lake Taupo erupted again. This time, the eruption was different, smaller than the Oruanui event, but in some ways more terrifying because of its speed and violence. Scientists call it the Hatape eruption, and it remains one of the most studied volcanic events in the southern hemisphere. By this time, humans had arrived in New Zealand. The Maori people wouldn't settle the islands for another 1,000 years, but the eruption was so powerful that it left marks in the historical records of distant civilizations. Chinese and Roman texts from this period mention unusual atmospheric effects. Red skies at noon, strange hazes that lasted for months, the sun appearing dimmer than normal. They didn't know what caused these phenomena, but we do now. It was Taupo, throwing debris into the upper atmosphere where it circled the globe. The Hatape eruption was notable for its pyroclastic flows. These flows were incredibly fast, among Baatwab, the fastest ever recorded in geological studies. They raced across the landscape at speeds approaching 500 miles per hour. At those speeds, there's no escaping, no running, no hiding. The flows covered over 50 square miles in minutes. What makes pyroclastic flows so deadly is their nature. They're not just hot gas. They're a mixture of superheated air, volcanic gases, and tiny particles of rock and ash. This mixture is denser than regular air, so it hugs the ground, flowing like a liquid. But it's hot enough to melt metal, typically between 200 and 700 degrees Celsius. Anything caught in these flows is incinerated instantly. The forests around Taupo were obliterated. Trees were snapped off at their bases or uprooted entirely. The flows crossed what is now Lake Taupo itself, actually traveling across the water surface for several miles before reaching the opposite shore. This is almost unheard of in volcanic eruptions. The flows were so hot and fast that they skipped across the water like stones, barely slowing down. After the pyroclastic flows came the lahars, volcanic mud flows created when the hot ash mixed with water. These lahars carved new channels in the landscape, carrying boulders the size of houses dozens of miles from the eruption site. They dammed rivers, created new lakes, and buried valleys under thick layers of volcanic mud. The eruption also produced what's called a Plinian column, named after Pliny the Younger, who described the eruption of Mount Vesuvius. This column of ash and gas rose miles into the atmosphere, spreading ash across the Pacific. The ash was pumice, light and full of air bubbles, and it floated on the ocean for months, washing up on beaches as far away as South America. When the eruption finally ended, the landscape was transformed. The caldera had expanded. New vents had opened. The lake had changed shape entirely. But what's fascinating is what happened next. Within years, life began to return. Seeds sprouted in the ash. Birds returned. The ecosystem started the slow process of recovery once more. This pattern, this cycle of destruction and renewal, wasn't unique to Taupo. It was playing out at volcanic sites around the world. Each eruption taught the same lesson. Life is resilient. Life adapts. Life continues. While Taupo was reshaping islands, something stirred in Japan. Southern Japan is a place of extraordinary beauty and danger. The islands sit along one of the most active volcanic zones on Earth, where the Philippine Sea Plate slides beneath the Eurasian Plate. This collision generates not just earthquakes, but some of the most powerful volcanic eruptions in recorded history. And 30,000 years ago, one of these eruptions reshaped the entire region. The Ira caldera eruption, also known as the Ira Tanzawa eruption, occurred in what is now Kagoshima Bay. Before the eruption, this area was likely a valley surrounded by mountains. After the eruption, it was a massive depression that the sea would eventually flood, creating the bay we see today. The eruption released about 170 cubic miles of material, making it one of the largest volcanic events of the last 100,000 years. At this time, humans were already living in Japan. Early hunter-gatherer populations had established themselves on the islands, following game animals and seasonal plants. They made tools from stone and bone. They knew how to make fire and build shelters. They had survived ice ages and all the challenges that came with them. But this eruption tested them in ways they had never experienced. The eruption likely began with warnings. Earthquakes would have shaken the region for weeks or months beforehand. Hot springs might have changed temperature or chemistry. Animals would have behaved strangely, their instincts detecting danger. Some human groups probably migrated away from the area, following these warning signs. Others stayed, either not recognizing the danger or unable to leave their territories. When the eruption came, it was catastrophic. The initial explosion threw a column of ash and gas into the stratosphere. The column was so large that it was visible from hundreds of miles away, a dark pillar connecting Earth to sky. The sound would have been deafening, a roar that continued for hours or days. Pyroclastic flows raced down from the eruption site, filling valleys and sweeping across plains. These flows were hot enough to turn sand into glass. They preserved the shapes of trees and plants in the ash, creating ghostly impressions that geologists study today. The flows reached the ocean, where they created massive clouds of steam that rose into the already ash-choked sky. The ash from Era spread across most of Japan. In places, it accumulated to depths of several feet. This ash layer is still visible today, a distinct grey band in geological exposures across the islands. Scientists use it as a marker layer, a reference point that helps them date other geological events. If something is above the Era ash, it happened less than 30,000 years ago. If it's below, it's older. The human populations in southern Japan were devastated. Archaeological evidence suggests that settlements in the region disappeared after the eruption. The survivors either died or migrated to safer areas. It would be thousands of years before humans returned to the Kagoshima area in significant numbers. The land needed time to heal, time for the ash to weather into soil, time for forests to regrow. But the eruption did more than just destroy. The volcanic ash, once it weathered, created some of the most fertile soil in Japan. Centuries and millennia later, when people did return, they found land that could support dense agriculture. The same force that had driven them away had also prepared a gift for future generations. These eruptions all share something, a pattern. When you look at all these eruptions together, something becomes clear. They're not random. They follow patterns, rhythms that play out over hundreds of thousands of years. Understanding these patterns helps us see supervolcanoes not as unpredictable monsters, but as natural processes that follow their own logic. It all starts deep underground, far below where we can see or touch. The Earth's mantle, the thick layer of rock between the crust and the core, is hot enough to flow like honey, though incredibly slowly. In some places, this rock is hotter than others. These hotspots create plumes, columns of rising molten rock that push upward toward the surface. When one of these plumes reaches the crust, it begins to melt the rock above it. This melted rock, magma, is less dense than the solid rock surrounding it, so it rises. It collects in chambers, vast underground reservoirs that can be miles across. Picture a balloon being slowly filled with water, except this balloon is made of rock and the water is molten stone at temperatures exceeding 1000 degrees Celsius. These chambers fill over thousands of years. The magma doesn't all arrive at once. It comes in pulses, in batches, each addition increasing the pressure slightly. The rock containing the chamber is strong, but it has limits. As the pressure builds, the rock begins to deform. It bulges upward. Cracks form. Groundwater seeping down into these cracks turns to steam when it meets the hot magma, creating even more pressure. This is why earthquakes happen before eruptions. The rock is fracturing, adjusting to the stress. These earthquake swarms can include hundreds or thousands of small tremors over weeks or months. They're warning signs, though ancient people wouldn't have understood them as such. Even today, predicting exactly when a supervolcano will erupt remains challenging. Eventually, the rock fails. A crack forms that connects the magma chamber to the surface. The pressure, released suddenly, drives the magma upward at incredible speeds. The eruption that follows depends on the composition of the magma. Thicker, stickier magma creates more explosive eruptions because gases can't escape easily. The pressure builds until it tears the magma apart in violent explosions. The time between eruptions follows patterns too. Yellowstone erupts roughly every about 600,000 to 800,000 years. Toba's eruptions were spaced about 400,000 to 5,000 years apart. These aren't exact intervals, but they're consistent enough to show there's a cycle. The magma chamber needs time to refill. The system needs time to build pressure again. Location matters as well. Supervolcanoes don't just appear anywhere. They happen at hotspots like Yellowstone, or at subduction zones where one tectonic plate slides beneath another, like in Indonesia and Japan. These are the places where the conditions are right for massive magma chambers to form. Understanding these patterns helps scientists monitor active supervolcano systems. They watch for the warning signs: ground deformation measured by satellites, changes in gas emissions from fumaroles and hot springs, earthquake patterns and depths, temperature changes in thermal features. Each piece of data helps build a picture of what's happening underground. But knowing the patterns also reveals something humbling. There are supervolcanoes active today, systems that are in various stages of their cycles. Some are building toward eruptions that won't happen for hundreds of thousands of years. Others might be closer than we think, which makes us wonder about the ones still sleeping. Just west of Naples, Italy, there's a place called Campi Flegrei. The name means burning fields in Italian, and it's an appropriate description. This area is dotted with volcanic vents, hot springs that bubble with sulfurous gases, and ground that's warm to the touch. Tourists visit to see the colourful mineral deposits and steam rising from cracks in the earth. But beneath this scenic landscape lies one of the most dangerous supervolcanoes on Earth. Campi Flegrei is a caldera, a massive depression created by an ancient eruption. But unlike Yellowstone or Toba, this caldera sits right next to a major population centre. More than 3 million people live within the potential danger zone. Naples itself, one of Italy's largest cities, sits on the edge of this volcanic system. This makes Campi Flegrei perhaps the most closely monitored volcano in the world. The last major eruption here happened about 40,000 years ago. Scientists call it the Campanian ignimbrite eruption, and it was massive, releasing around 60 cubic miles of material. The eruption affected climate across Europe and the Mediterranean. Ash layers from this eruption have been found as far away as Russia. Some researchers believe this eruption may have contributed to the extinction of Neanderthals in Europe by destroying their habitats and resources. But Campi Flegrei hasn't been quiet since then. In 1538, there was a smaller eruption that created a new volcanic cone called Monte Nuovo, New Mountain. The eruption lasted for 8 days, forced the evacuation of the town of Pozzuoli, and dramatically changed the local landscape. This showed that the system was still very much alive. What makes scientists particularly concerned about Campi Flegrei is something called bradyseism. This is the slow rising and falling of the ground above the magma chamber. The area around Pozzuoli has risen and fallen by several feet over the past decades. Ancient Roman ruins that were once at sea level are now above the water. The harbour where Roman ships once docked is now dry land. This movement shows that the magma chamber beneath the surface is active. When the ground rises, it suggests that magma or volcanic gases are filling the chamber, pushing the ground upward. When it falls, it indicates the pressure has decreased, either because magma has moved elsewhere or gases have escaped. These cycles of rising and falling have been happening for centuries, but they've become more pronounced in recent decades. The ground rising isn't the only concern. Earthquake activity in the area has increased. These aren't large earthquakes. Most are too small to feel, but there are thousands of them. They indicate stress in the rock, movement in the magma chamber below. Gas emissions have also changed, with more carbon dioxide and sulfur dioxide being released from vents across the caldera. Scientists monitor all of this carefully. They use satellites to measure ground deformation to within millimeters. They have seismometers recording every tremor. They sample gases regularly to detect any changes in chemistry. They drill into the caldera to study the rocks and understand the structure of the magma chamber. All of this data helps them assess the risk. The key question is, when will Campi Flegrei erupt again? Nobody knows for certain. The system could remain in its current state for thousands of years, or it could escalate relatively quickly. But there's something closer to home that's stirring too. Yellowstone National Park receives millions of visitors every year. They come to see Old Faithful erupt on schedule, to watch bison herds graze in meadows, to photograph the brilliant colours of Grand Prismatic Spring. They walk on boardwalks over ground that's literally boiling just inches below the surface. Most have no idea they're standing inside one of the most powerful volcanic systems on Earth. Beneath the beauty and tranquility, something is very much alive. The same hotspot that caused those 3 massive eruptions over the past 2 million years is still there, still active, still pushing heat and magma toward the surface. The difference is that right now, the system is in between eruptions. But that doesn't mean nothing is happening. Scientists monitor Yellowstone constantly. They have seismometers scattered throughout the park that record every earthquake. And there are many earthquakes. Yellowstone experiences between 1,000 and 3,000 earthquakes per year. Most are so small you'd never feel them, registering below magnitude 3. But occasionally, larger swarms occur. In 2017, a swarm of more than 2,400 earthquakes hit the area over several months. The largest was magnitude 4.4, strong enough to feel but not dangerous. These earthquake swarms are normal for Yellowstone. They happen when magma or hydrothermal fluids move beneath the surface, fracturing rock and creating stress. Each earthquake is like a small adjustment, the ground settling around the forces moving below. Scientists study the patterns carefully, looking for anything unusual that might indicate a change in the system. The ground at Yellowstone also moves. GPS stations measure it rising and falling by several inches over the course of years. Between 2004 and 20, an area north of Yellowstone Lake rose by about 10 inches. This was caused by magma moving into the chamber about 6 miles below the surface. Then, just as scientists were getting concerned, the uplift stopped and the ground began to sink again. This kind of breathing is normal for volcanic systems. Thermal features change too. Geysers alter their eruption schedules. Hot springs change temperature or color. New steam vents open while old ones close. In Twinard, a previously dormant geyser called Steamboat, the world's tallest active geyser, suddenly became very active, erupting dozens of times in a year after being mostly quiet for decades. These changes reflect the dynamic nature of the hydrothermal system, which is powered by heat from the magma below. Gas emissions tell another part of the story. Carbon dioxide seeps from the ground across large areas of the park. In some spots, the concentration is high enough to kill trees and create bare patches in the forest. Scientists measure these emissions carefully because changes in gas output can indicate changes in the magma chamber. So, should we be worried? The short answer is no, at least not immediately. All the activity at Yellowstone is consistent with a volcanic system in between eruptions. Scientists see no evidence that an eruption is imminent. The magma chamber is partially molten, but most of it is still solid rock. It would take a massive influx of new magma to trigger an eruption, and there's no sign of that happening. The longer answer is more complex. We know Yellowstone will erupt again eventually. The hotspot beneath it hasn't gone away. The cycle that produced 3 massive eruptions will likely continue, but that eruption might not happen for hundreds of thousands of years. So what would happen if one woke up today? Imagine waking up one morning to news that Yellowstone has shown signs of an impending eruption. Not the small changes scientists see regularly, but something major. A massive earthquake swarm. The ground rising several feet in a matter of weeks. Gas emissions increasing dramatically. What would happen next? How would the world respond? First, understand that a supervolcano eruption wouldn't happen without warning. The signs would build over months, or possibly years. Scientists would see the magma chamber inflating as new molten rock pushed in from below. Earthquakes would become more frequent and stronger. The thermal features would go haywire, with geysers erupting at unprecedented rates and new vents opening across the caldera. Authorities would begin evacuations long before any actual eruption. The immediate area around Yellowstone, including parts of Wyoming, Montana, and Idaho, would be cleared. We're talking about potentially millions of people needing to relocate. Major highways would be clogged. Emergency services would be overwhelmed. The logistics alone would be staggering. but it would be necessary. If the eruption happened, the first hours would be the most dangerous for people nearby. Pyroclastic flows would race across the landscape at hundreds of miles per hour, but their reach would be limited to perhaps 100 miles from the eruption site. Anyone who hadn't evacuated would have almost no chance of survival. The flows would be followed by lahars, volcanic mudflows that could travel much farther, especially down river valleys. Then comes the ash. A Yellowstone eruption would blanket much of North America in volcanic ash. States like Montana, Wyoming, Colorado, and the Dakotas could receive several feet of accumulation. As far away as the Mississippi River, there might be inches of ash coating everything. This ash would cause immediate problems. It's not like snow. It doesn't melt. It's heavy, abrasive, and dangerous to breathe. Infrastructure would fail quickly. Ash would clog air filters in vehicles and machinery, causing engines to seize up. Power plants would struggle to operate. Water treatment facilities would be overwhelmed trying to filter ash from water supplies. Roads would become impassable, not just from the weight of ash, but because it turns slippery when wet. Roofs would collapse under the weight. The economic impact would run into trillions of dollars. Agriculture across the central United States would be devastated. Crops buried under ash would be lost. Livestock would struggle to find food and clean water. The ash in their lungs would cause respiratory problems. The food supply chain would be disrupted on a scale never seen in modern times. Food prices would skyrocket globally as one of the world's major agricultural regions went offline. But here's where modern technology makes a difference. We have global communication networks. We can coordinate relief efforts across continents. We have the ability to transport food and supplies quickly. We understand what's happening and why. Ancient people had none of these advantages. They couldn't predict eruptions or understand their causes. They couldn't call for help from other regions. They had to survive with only what they could carry. The volcanic winter would affect the entire planet, but we'd be better prepared for it. Greenhouses could continue food production. Strategic reserves could be deployed. Scientists could model the climate impacts and help governments prepare. We'd face immense challenges, yes, but we wouldn't be helpless. The eruption would be a global crisis, but not an extinction event for humanity. We'd adapt, as we always have. We'd rebuild, learn, and prepare better for the future. But here's what we've learned from every eruption. Every supervolcano eruption tells the same fundamental story. Destruction followed by recovery. Death followed by rebirth. The pattern repeats across millions of years and thousands of miles. And in that pattern, there's something profound about the nature of life itself. Life doesn't give up. It can't give up. That's not how evolution works. Even in the most devastating circumstances, in landscapes that seem completely dead, life finds refuges. These refuges are the key to understanding how recovery happens. They're the seeds from which entire ecosystems rebuild. A refuge might be a valley that somehow escaped the worst of the pyroclastic flows. It might be an island offshore where ash didn't fall as heavily. It might be a cave system where animals sheltered from the choking air. Or it might be something as simple as a deep lake where fish survived because the water insulated them from temperature changes. These refuges exist in every catastrophe, and they preserve the diversity needed for recovery. The timeline of recovery follows a predictable sequence. First come the pioneer species, the tough ones that can survive in harsh conditions. These are often grasses, mosses, and lichens. They don't need rich soil. They can grow in pure ash if there's enough moisture. Their roots begin the slow work of breaking up the compacted ash, creating spaces for air and water. When these pioneer plants die, they add organic matter to the sterile ash. This is the beginning of soil formation. It's a slow process, taking decades or centuries, but it's essential. Without soil, more complex plants can't establish themselves. Without complex plants, herbivores can't return. Without herbivores, predators have nothing to hunt. Next come the insects. They're attracted to the pioneer plants, and they bring something crucial. They bring mobility. Insects can fly dozens or hundreds of miles, carrying pollen between isolated plant populations. They pollinate flowers, helping plants reproduce. They also become food for other animals, forming the next link in the rebuilding food chain. Birds follow the insects. They can cover vast distances, and they bring seeds in their digestive systems or stuck to their feathers. Each bird is like a tiny delivery service, bringing genetic diversity from distant refuges to the recovering zones. The seeds they deposit grow into new plants, increasing the variety of species in the area. Small mammals come next. Rodents, rabbits, and similar creatures move into areas where there's enough vegetation to support them. They dig burrows, which further breaks up the ash and improves drainage. They eat plants and spread more seeds. They become prey for the predators that will eventually follow. Large herbivores take longer to return. They need established grasslands or forests to support their populations. But when they do return, they transform the landscape. Their grazing patterns shape plant communities. Their droppings fertilize the soil. Their migrations connect different areas, spreading seeds and nutrients across vast distances. Finally come the large predators. They need healthy populations of prey animals to survive. Their return signals that the ecosystem has reached a certain level of stability and complexity. The presence of apex predators is actually a sign of health. It means the entire food web is functioning. This sequence plays out after every eruption. It played out after La Garita, after each Yellowstone eruption, after Toba, after Taupo and Ira. The details vary, the species involved change, but the pattern remains constant. Life rebuilds itself from the smallest organisms upward, layer by layer, slowly transforming dead landscapes into living ones. And in that pattern, there's something beautiful. It seems strange to think of supervolcanoes as giving gifts. They destroy so completely, kill so efficiently, disrupt so thoroughly. But over time, over the long centuries and millennia after the immediate catastrophe, these violent events leave behind something valuable. They shape the world in ways that benefit life. The most obvious gift is soil. Volcanic ash, once it weathers and breaks down, creates some of the most fertile soil on Earth. The ash is rich in minerals that plants need: phosphorus, potassium, calcium, and dozens of trace elements. These minerals are locked in the volcanic glass and rock. But as water and acids from plant roots break them down, they become available for uptake. This is why volcanic regions, once they've recovered, often become agricultural heartlands. The slopes of Mount Vesuvius in Italy are covered with farms and vineyards. The soil is so productive that people are willing to live with the risk. The valleys around Yellowstone, once the ash has aged into soil, support rich grasslands. The fields of Java and Sumatra, built on volcanic deposits, feed millions of people. The danger and the bounty come from the same source. Supervolcano eruptions also create geothermal resources. The heat that powered the eruption doesn't disappear. It remains below the surface, warming rocks and water. This heat can be harnessed. Iceland gets most of its electricity and heating from geothermal sources, all linked to its volcanic nature. New Zealand uses geothermal energy extensively. Yellowstone's thermal features, while protected as natural wonders, represent enormous energy potential. Hot springs and geysers become ecosystems unto themselves. The water is heated from below and enriched with minerals dissolved from the rocks. Unique bacteria and archaea live in these extreme environments, organisms that can't survive anywhere else. Some of these microorganisms have given us important scientific insights and even useful enzymes for research and medicine. The calderas themselves often become important water resources. Lake Taupo provides drinking water and supports fisheries. Crater Lake in Oregon, formed by a volcanic collapse, is one of the purest bodies of water in North America. These lakes are often deep and cold, providing unique habitats for aquatic life. Volcanic landscapes also create incredible beauty. The dramatic topography, the colorful mineral deposits, the steam rising from vents, all of this draws people. Tourism becomes an economic resource. Yellowstone alone generates billions of dollars in economic activity. The volcanic islands of Hawaii, Iceland, and New Zealand are destinations precisely because of their volcanic nature. Perhaps less obvious is how supervolcano eruptions drive evolution. The catastrophes create new ecological niches. Species that survive often evolve rapidly to fill the empty spaces left by extinct competitors. The genetic bottlenecks, while reducing diversity in the short term, can lead to rapid adaptation. Populations that survive extreme conditions carry genes for resilience, and those genes become more common in future generations. The mineral deposits created by volcanic activity are economically important too. Many valuable ores form in association with volcanic systems. Copper, gold, silver, and rare earth elements concentrate in certain types of volcanic rocks. The mining industry follows volcanic belts around the world, extracting resources that modern technology depends on. Even the atmospheric effects, devastating in the short term, play a role in Earth's climate regulation over geological time. Volcanic aerosols in the stratosphere reflect sunlight, cooling the planet temporarily. This has happened many times throughout Earth's history, acting as a natural brake on warming trends. Which brings us full circle. We started this journey by drifting into the deep places of Earth, where forces beyond imagination have shaped every living thing. We've traveled through millions of years, witnessed catastrophes that reshaped continents, and watched life rebuild itself again and again. Now, as we near the end of our exploration, it's worth pausing to consider what all of this means for us. Human existence is a tiny sliver of time compared to the vast geological cycles we've discussed. Our species has been around for perhaps 300,000 years. Modern civilization, with its cities and agriculture and technology, spans maybe 10,000 years. The supervolcano eruptions we've explored stretch back millions of years. We are newcomers to this ancient dance between Earth's fire and life's persistence. Yet we're also participants in this story. We lived through Toba, even if we barely survived it. Our ancestors felt the ground shake and watched the sky turn dark. They made choices that determined whether our species would continue or fade into extinction like so many others. The fact that you're here, reading these words, means those ancient humans made the right choices. They endured, they adapted, they survived. This perspective is both humbling and empowering. Humbling because it reminds us how small we are in the grand scheme of things. The forces that created these eruptions don't care about human civilization. They follow their own rhythms, playing out over timescales that make our entire history seem like a brief moment. We build our cities and our lives on a planet that is fundamentally dynamic, restless, constantly changing. But it's also empowering because it shows us what life is capable of. If tiny populations of humans could survive Toba with nothing but stone tools and fire, what can we accomplish with all our modern knowledge and technology? We can monitor volcanic systems, predict eruptions, coordinate global responses. We have the ability to preserve knowledge, to learn from the past, to prepare for the future. The supervolcanoes that shaped our past are still with us. Yellowstone still breathes beneath its geysers. Campi Flegrei still rises and falls on the edge of Naples. Toba still steams in its massive caldera lake. These systems haven't disappeared. They're simply resting, building pressure for eruptions that might happen tomorrow or might wait another 100,000 years. This uncertainty is part of living on Earth. We can't prevent these eruptions. We can't shut down the geological processes that create them. What we can do is understand them, respect them, and prepare for them as best we're able. We can appreciate that the same volcanic activity that brings danger also brings gifts: fertile soil, geothermal energy, mineral resources, incredible beauty. There's a certain peace in accepting our place in this larger story. We're not separate from nature, observing it from the outside. We're part of it, shaped by the same forces that shape everything else. The calcium in our bones might have come from ancient volcanic ash. The iron in our blood was forged in the heart of exploding stars and brought to Earth's surface by volcanic activity. We are literally made of the same stuff as the planet itself. And like the planet, we're resilient. We adapt. We recover from setbacks. We find ways forward even when the path seems impossible. That's not just a human trait, it's a life trait, something we share with every organism that has ever faced catastrophe and survived. How these ancient forces still shape our world today. So, here we are, at the end of our journey through fire and time. We've walked through eruptions that nearly ended life as we know it. We've watched ecosystems collapse and rebuild. We've seen how the most destructive forces on Earth can also be the most creative, shaping landscapes and driving evolution in ways both terrible and beautiful. The supervolcanoes we've explored aren't relics of the distant past. They're active parts of our living planet. Right now, beneath Yellowstone, magma chambers are slowly refilling. Under Campi Flegrei, the ground is rising and falling with the rhythm of geological forces. In Sumatra, where Toba once nearly ended humanity, life flourishes in the rich soil created by ancient catastrophe. The cycle continues, as it has for billions of years, as it will for billions more. What's remarkable is not that these eruptions happen, but that life persists through them. Every time Earth throws its worst at the living world, life finds a way through. It squeezes through the narrowest gaps between extinction and survival. It rebuilds from the smallest refuges. It transforms dead ash into living soil. It adapts, evolves, and eventually thrives again. We humans are part of this story of resilience. We carry in our genes the memory of Toba, the moment when we nearly disappeared. But we didn't disappear. We survived. And from that tiny population of survivors, we've grown to inhabit every corner of the planet. We've built civilizations, created art and science, learned to understand the very forces that once nearly destroyed us. This understanding brings both comfort and responsibility. Comfort because it shows us that life, including human life, is tougher than we might think. We've been through worse than anything our modern world faces, and we're still here. Responsibility, because we now have the knowledge and tools to protect ourselves and other species from future catastrophes. The next supervolcano eruption will happen. It might be in our lifetime, or it might be thousands of generations from now. We can't stop it, but we can prepare for it. We can monitor the warning signs. We can plan evacuations. We can stockpile resources. We can work together as a global community to weather the storm. But for now, tonight, as you drift towards sleep, take comfort in the deeper pattern. The pattern that shows how life always finds a way forward, how destruction creates space for new beginnings, how the forces that seem most frightening are also the ones that created the world we love. The fertile valleys, the majestic mountains, the hot springs and geysers, the rich soil that feeds us, all gifts from the fire beneath. If you found peace in this journey through deep time, if these stories of resilience and renewal have brought you calm, I'd love for you to like this video and subscribe to the channel. Share it with others who might find comfort in understanding our place in the vast sweep of Earth's history. Tomorrow, we'll explore another corner of the natural world together, another story of wonder and science that might help you drift into peaceful sleep. And before you close your eyes tonight, maybe leave a comment about what surprised you most in this journey. Was it the scale of these eruptions, the resilience of life, the fact that we're all descendants of those Toba survivors? Rest well, knowing that you're part of an ancient, ongoing story. A story written in stone and ash, in genes and memory, sleep peacefully.